Okay, now I'm going into the last chapter, chapter 13, on boundary value problems as opposed to the initial value problems from a previous chapter. So still dealing with ordinary differential equations. And we're just going to cover the first two sections of this chapter. So 13.1 on the shooting method, and then 13.2 on finite difference methods for these BVP. So what is a two-point boundary value problem? So I'll give you the general form. So what we have is a second order ODE as opposed to the first order we had before. Um, so y double prime is equal to some function of an independent variable x, and then also the solution y itself and its first derivative. And the problem is defined on a bounded interval, AB. And unlike initial conditions that we've had before, we have these boundary conditions. So at the left endpoint A, the solution is equal to alpha, and at the right endpoint B, the solution is equal to some specified value beta. So this is why it's a two-point boundary value problem. The solution is specified at these 2 points, and it satisfies this ODE in between. Now, before talking about solution methods of any kind, there are some assumptions that we impose to guarantee a unique solution. So the first one won't be any surprise that the function f and df dy and df dy prime are continuous in these variables. So on domain containing x in the interval AB, and then y and y prime are allowed to be assume any value that so if the domain is under consideration, f and v's partial derivatives must be continuous. And a particularly important condition, this one will be relevant for one of the homework problems, df dy must be positive on the domain of a problem. Again, x between a and b, and then y and y prime can be anything. And finally, df dy prime must be bounded. So it's not allowed to shoot off to infinity. So I'm going to specify this x in AB and y and y prime or any real numbers. Okay, so when I say on a domain, it's this domain that I'm referring to. So keep in mind this assumption is very important. That df/dy must be positive, and that helps ensure a unique solution. Okay, now we're going to see two very different approaches for solving this kind of problem. So one under consideration in this section, 13.1, is the shooting method. The shooting method solves this boundary value problem, so abbreviated BVP as opposed to IVP for initial value problem. So the shooting method solves this BVP, converting it to an initial value problem, or IVP, where the ODE is the same, f of x, y, y prime, and then the first boundary condition at x equals a is the same. But instead of specifying a value at the endpoint, y equals b, we're going to specify a second initial condition, y prime at a is equal to t, where t is an unknown value. So the idea is, this is what's called a shooting method. We are when x equals a, we're at alpha. When x gets to b, we want to be at beta. So the idea is we try to find the right slope. So it's almost like we're aiming for the value beta. So we try to find the right slope for the solution at the left endpoint, so that the trajectory of a solution as x goes from a to b will take us from alpha to beta. So that's why it's called a shooting method. We're trying to find the right angle at which to fire, if you will, so that we'll hit the target at the other end, which is beta. So that way we can leverage all that we've learned about numerically solving initial value problems to solve this boundary value problem. So we could use a time-stepping method such as Euler's method or Runge-Kutta, something like that. Now, one thing to keep in mind is we're accustomed to solving initial value problems of y prime is a function of t and y. So this requires rewriting the ODE as a first-order system where we have two variables and okay. So y1 prime. Now, this is a superscript, not an exponent. Okay, I'm not raising something to a first or a second power. That's equal to y2, and then y2 prime is equal to f of x, the independent variable, and then y1, superscript y1, y sup 2. So y1 corresponds to y, and y2 represents y prime. So now we have a system involving only first derivatives of these two variables, y1 and y2. So you can apply a time-stepping method to solve this system of ODEs. The initial conditions are y1 of a is equal to alpha, so first boundary condition, and y2 of a is equal to this unknown value t. So the idea is you can select a value of t and go ahead and solve this initial value problem with these initial conditions of this choice of t, and see if you if your value of your solution of y1 at b is equal to beta, like you want it to be. So you can think of it as the goal is to find the value of t such that y1 at b, and so what I'll do is I'm going to call this value that we're looking for, I'll call it t star, and I'm going to let this solution y1 have a parameter, t is a parameter. So the idea is what this represents is okay, I'll write it down here, where y1 b of xt is the solution obtained from the initial condition y2 of a is equal to t. So what I mean by all this is, once we choose initial value for y2, we go ahead and solve a problem, and we evaluate y1 at x equals b. We want this to be equal to beta to match the boundary condition. So So since we're looking for a value of t star, that satisfies this equation, in other words, this function of t is equal to 0, what we're effectively doing, we're finding a root of this function f of t. So you can use any root finding method to find a root of this function. It's just that evaluating this function is quite a chore, because in order to evaluate this function at any value of t, you must solve a whole initial value problem and then evaluate your numerical solution at x equals b, and then subtract beta, and hopefully that will be converging to 0. So that's the idea, is that we were trying to find a root of this function. Okay. Now, how this is done breaks down into two categories. We have two types of boundary value problems we can consider: linear and nonlinear. A linear problem, we'll actually see, is rather straightforward to find the value of t that works, and I'll show you that in a moment. When it's a nonlinear case, then this is a nonlinear function of t, so you have to use a root finding method, such as Newton's method or fixed point iteration, something like that. And that's something I'll discuss in the next video. So you have a root finding method wrapped around a very expensive function to evaluate. Okay, now for a linear problem, I can specify what the ODE looks like with a little more detail than in a general case. So a linear BVP, it's linear in the variables y and y prime. So this is this form: y double prime is equal to some coefficient p of x depends only on x times y prime plus another function q of x, y plus some function r of x. So what happens is df dy is equal to p of x, and df dy prime, df dy is equal to q, df dy prime is equal to p. So we're able to determine those partial derivatives of f very easily. So therefore, we're going to assume that p of x is positive. Sorry, I apologize. I keep getting y and y prime mixed up here. Q of x is positive, since df dy being positive, ensures that we have a unique solution, as I mentioned at the very beginning. So this coefficient must be positive. This coefficient, p of x, it at least has to be bounded to guarantee a unique solution. Okay. So, whereas for nonlinear problems, an iterative process is required to find the magic value of t that will hit our target of beta. For a linear problem, no such iteration is required, and here's why. Okay. Okay. So we break it down into two other linear boundary value problems. And I'm going to call the solutions of these y1 and y2. So y1 solves y double prime. So the ODE will be exactly the same. And the boundary conditions will be y of a is alpha, taken from the original problem. But then we're going to assume that y prime of a is equal to 0. Okay, so this one's independent of whatever value of t we pick. And then y2 of x will solve this problem. So y double prime is equal to, ODE starts out the same, but we do not have the r of x term. And you'll see why momentarily. So y of a will be equal to 0, and y prime of a is equal to 1. Yes, 1. Okay, now how does that help us? So then we just let y, our solution y, be equal to y1 plus t y2. So the thing is, y1 is already a solution of our ODE. Now, if we take this linear combination, y1 plus any multiple of y2, whatever that multiple might be, so y2 satisfies this. So this linear combination will satisfy the original ODE, because if I were to substitute sorry, it's being uncooperative again. So what I have is y1 plus t y2 double prime is equal to p of x y1 plus t y2 prime plus q of x y1 plus t y2 plus r of x. And the thing is, y1 plus py1 prime plus qy1, sorry, y1 double prime equals py1 plus qy1 plus r. So that is already satisfied. And then, basically what I'm doing is I'm taking this equation and I'm adding to it t times this one. So since y2 double prime is equal to p y2 prime plus q y2, those terms match up, and then multiplying by t does not mess with that. So for any t we choose, y of x is a solution of our original ODE. At the boundary, we have y of a, which is equal to y1 of a plus t y2 of a. Well, y1 of a is equal to alpha from the first problem, and then y2 of a is equal to 0. So it automatically satisfies the first boundary condition. And then y of b is equal to y2 of b plus y1 of b plus ty2 of b. Now, y okay. I can't do anything with that yet. Y prime of a. So that is equal to y1 prime of a plus t y2 prime of a. Now y1 prime of a is equal to 0, and then y2 prime of a is equal to 1, so that's just t. Okay. Now, this is supposed to equal beta, based on the boundary condition. So what I could do is, I can take this equation, because y1 of b and y2 of b are known once I've solved these. I can just solve for b. Now not b. t. We're solving for unknown parameter t, and that will depend on beta. Y1 would be, Y2 would be. I'm not doing it here, it's in the homework. And we need an assumption Y2 would be, must be non-zero. One of the homework problems considers the possibility of Y2 would be equaling 0. And it turns out that this will contradict the assumptions we're making about the original problem. So that's all I'm going to say about this right here, that you would use the homework to finish off a process of finding t. But the point is, once we solve these problems, all the real work is done. It's very easy after that to obtain the value of t from requiring y of b to equal beta. Okay, now, but just as an example, so we have this boundary value problem. Y double prime is 2y prime minus y plus x e to the x minus x. So x e to the x minus x is equal to this, that's the r of x from a general linear problem. And boundary conditions are specified at x equals 0 and x equals 2. So a is 0, b is 2. So alpha is 0 and beta is equal to minus 4. So first we solve the initial value problem. Same ODE. With boundary conditions y of 0, 0, y prime of 0 equal 1. And this is an ODE that can be solved analytically. I'll just type out what the solution is. So y1 of x turns out to be 16 x cubed e to the x minus x e to the x plus 2 e to the x. Sorry, it should be a minus x plus 2 e to the x minus x minus. I'm looking at my notes while I'm typing. Okay. I apparently cannot type today. That's really weird. Okay. 2 e to the x minus 2. Not sure why I was keep getting an m there, because that's definitely not what I was typing. Okay. So that's y1. Then we solve this related initial value problem. Y double prime is equal to 2y prime minus y. And y of 0 equals 0, which is always the case, regardless of what alpha is from original problem, which is that alpha happens to be 0. Y prime of 0 is equal to 1. That gives us y2 of x is equal to just x e to the x. Then what we have is y of x is equal to this solution, y1, plus t times the other solution, x e to the x. And if I substitute x equals 0 in here, both parts, so that part and that part, satisfy that the condition that you plug in x equals 0, you get 0. So it automatically satisfies the left boundary condition. But then we plug in y of 2. So that's equal to y1 of 2 plus t y2 of 2. So if I plug in x equal to 2 in here, then for the y1 part, what I end up getting is for 4/3 e to the x, or e squared rather, because x equals 2, minus 4, because I plug in x equal 2. These two terms cancel out, and I get minus 2 and minus 2. And then I plug in x equal 2 over here also, and I get 2e squared, but all that's multiplied by t. And that has to be equal to minus 4. So now this equation has to be solved for t. Now the minus 4s on both sides, those cancel out. I have a coefficient of e squared of 4/3 here and 2t here. So if we set t equal to minus 2/3, then we've satisfied the boundary conditions. So that would cause this term to cancel out with this, because I have 4/3 here and I have minus 4/3 here, all times e squared. Only the minus 4 remains, which is what we're trying to match over here. So we see here, by solving these two other linear initial value problems by whatever method, these could be solved analytically, but other ones would need to be solved numerically using the time-stepping method of your choice. But once you have those solutions by whatever method, then you can go ahead and solve for value of t so that the original boundary value problem is solved. Now, in this case, once we solve these two problems, there's very little work to do after that. But in the case of a nonlinear boundary value problem, an iteration will be required, because we're not able to just combine solutions in this way due to the nonlinearity. So that's what I'll take up next time. One thing I want to mention real quick, so I'll go to my announcements section. Final exam. So there's our oral exam where I can ask you whatever conceptual questions. So it's kind of like an oral version of a lightning round from a midterm. Using whatever technology you prefer. So I've made use of Skype or Zoom or Microsoft Teams, that's that sort of thing, or coding project on the assignments page. It's already been posted. It's been there all semester long. And that is actually on 2-point boundary value problems. So as I go through this chapter, you can take a look at that. The last homework, homework 9, if you decide to do that, also concerns boundary value problems. The oral, if you choose that option, that will be comprehensive. So I'll be asking questions from over the entire semester. Don't wait too long to make your choice, and let me know which you'll pick, because for those who choose the oral, we'll want to schedule that. And all work must be completed by Thursday, May 14th, at any time during that day. So, because grades will be due the following Monday, the 18th, and I'll need those few days to finish grading, because something tells me I'm going to have a whole lot of homeworks to look at. Okay, so please keep that in mind. So you have some time to think about it, and let me know what you'd like to do. There are 14 of you altogether, so I want to make sure that everyone is accounted for. So that's it for today, and we'll take up shooting method for nonlinear BVP next time.